What do we do first with a limit? Always.
Plugging.
Yes, 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 absolutely. So where does x go? Where are my props? My props have to be ready here. Where does x go?
Infinity.
Good. Where does, I should have started with the power, but it doesn't matter. Where does this go when x approaches infinity? Where does this go? Anyone?
0.
Careful. So I have a number minus x when x approaches infinity.
This is negative infinity?
Sure, of course. Okay. So now let's analyze what we have. We have the situation of infinity raised to negative infinity. I shouldn't even write this. It's not really legal for me to write this, but I have to write it so I can explain what I'm doing. Well, we know that there is a different setting, a different presentation of this. What is the other presentation of this? Is there any other way of writing this?
Infinity over infinity.
So a raised to negative n. How do I write this in another way?
A divided by n.
No, it's 1 over a raised to m.
Good. That's my n, I'm sorry, but you're right. M or n, the same thing. Yes. So this is one of the exponential rules that we've been using over and over. Please. Okay. So this is 1 over infinity raised to infinity. Good. Can anyone tell us what does this mean?
Super infinity?
Exactly. Good. Where does this go?
0.
Thank you. Done. I don't have to do anything. No action required. Good. Very good pick. Thank you. It's a good example. Okay, anything else? Allow me to choose one. Or if you want to choose one. I would like to illustrate one more example with
68.
68. Let's take a look at 68. Okay, did we do 68? I don't want to do the same thing unless you want me to. Did we do 68 last time? I don't remember it. Okay, perfect. Good. When x approaches 0, where is this going?
Zero.
We have to remember the graph. We have to remember the graph of 1 over x. If we don't have the graph of 1 over x clear in our mind, it will take us a long time to figure this out.
We're all thinking, is it undefined? But
well, you're right. It's kind of positive or negative infinity. From one side is negative, from the other side is positive. Good. Where does this go?
1.
Very good. So we do have an indeterminate case, which is 1 to infinity. Or negative, it doesn't matter. Still the same. 1 to infinity. Good. So it's the power. It's the most cumbersome, and it has several steps. What is the step number 1? So let's go through the steps again. What is step number 1 here? What did we do last time? I'm sorry?
Domain.
No. What did we do last time? What was the first step we did last time with a problem like this? Anyone? Thank you very much. Y equals cosine x raised to 1 over x. Apply natural log and write 1 over x natural log cosine x. Awesome. Great job. Who said that? Gia. Okay. I thought I just imagined. Thanks. Okay. Number 2. Awesome. Anyone remembers number 2? Step 2. After we apply natural log. Great job. Thank you. Anyone?
Apply the limit.
Thank you very much to both sides. Awesome. So limit, was it Sean? Yes. Of natural log y equals the limit on this side and limit on this side. Limit as x approaches 0 from, and I'm going to write it as natural log of cosine x over x. Great job. Good. Now I'm focusing on this. Although you could say, wait a minute. This is not where, okay, wait till the end and you'll see what happens. And I'm sure you're anticipating that. Okay. Where does cosine go when x approaches 0? You already told me this is 1. Where does this whole thing go when x approaches 0? Where will this go? Natural log 1.
0.
Thank you. Where does this go?
There.
Good.
0.
Are you happy? I'm very happy. Why? Why am I happy with the outcome so far?
That's also an indeterminate case. We know how to work.
Yes, when we use L'Hopital's rule. Awesome. That's it. So limit as x approaches 0. The derivative of the denominator is
1.
Excellent. How do I differentiate natural log?
1 over, and in this case, cosine x times negative sine x.
Brilliant. Thank you, Brian. Okay, perfect. So now I have the limit of as x approaches 0 from sine over cosine, which is tangent, and I'll put the minus outside. Limit from tangent as x approaches 0. Good. So can anyone give us the limit as x approaches 0 from tangent?
It's 0 because sine x is 0.
Awesome. Brilliant. Okay, then. Now in step 3. What do we do in step 3?
You take the first part of the second step and the last step of the second step?
Brilliant. Thank you, Rihanna. First and last. Good. At this point, all these functions are continuous. I'm going to swap the operators. Okay? So then I have natural log of the limit as x approaches 0, and y I can put it in. Cosine x raised to 1 over x. And now I'm going to ask myself, what could this be? And that's the answer.
One.
Only natural log 1 is 0. Or you say e raised to 0 equals what? Well, has to be 1. That's why this piece must be 1. Great pick. Moving on. Okay, allow me to continue with 4.5. And then we'll go back to 4.2. In 4.5, we have what we've been doing already. I only have to show two things about the slant asymptotes and about graphs with holes. That's it. Because we've been graphing and graphing and graphing already. Okay, so 4.5, two things. Graphs with holes. And no, I'm not talking about piecewise defined functions. Those have holes in them as well. We already talked about that in chapter 2 and over. And the other one, the other topic here, slant asymptotes. So I'm going to give an example from each. I'm going to let you choose from this, but I'll get to it in a moment. I want to graph a function with holes. Or hole. Not necessarily. It don't have to be many. Okay, so here's an example of such a function.
You're still sharing your screen.
Thank you so much. So sorry. Okay, sorry. So let me go back now. So in 4.5, we've seen almost everything except these two concepts, because as you've noticed, we graphed and our first question was, second question was, all this. This is it. So now, two concepts that I did not get the chance to present. Graphs with holes and slant asymptotes. They may be in the same function or separate. So first I'm going to start with an example with a graph with holes. So x squared minus 3x plus 2. Can anyone identify this function for us? Say what type it is, this function, whole thing? Anyone? Please.
You're looking at polynomial?
But when you read it, you will say x minus 1 over x squared minus 3x plus 2. No polynomial has a ratio of functions, right? So if you say this, yes. If you say this, yes. But a ratio of two polynomials is a different function. How do we call it? I refuse to believe that no one remembers the name of this function.
All I remember is we used the quotient rule, but
Good.
don't know what type.
So is there another name for a quotient? Is there a synonym for quotient? Good. So no matter what you're asking or what we are asked to do with this function, I have to start with the domain. So when I factor the denominator, can anyone give us the factored form?
X minus 2, x minus 1.
Very good. Awesome. So regardless of what the numerator has, I have to state two restrictions. And the restrictions are?
X can't equal 2 and x can't equal 1.
Excellent. After I state the restrictions that give us the domain of this function, in other words, negative infinity 1, union 1 to 2, union 2 to infinity, I have to simplify the function. And what is the simplified form then?
Is it 1 over x minus 2?
Excellent. That's it. 1 over x minus 1. So notice two things happening here.
Isn't it two?
Two, of course. Notice two things are happening. One factor that goes away, that will be the whole of the graph. Because the factor goes away. The function is still undefined at 1. And we will have to determine what to put in here by simply replacing 1 in the final simplified form. If I replace it here, I get 0 over 0. That doesn't mean anything. So 1 minus 2 is -1, so I get -1. So the whole in the graph is always obtained when a factor goes away. The function is undefined at 1, but it turns out that that factor gets removed by simplifying it from top and bottom. So this becomes a whole in the graph. However, x equals 2 is still a vertical asymptote, not still, because it finds its way in the final form of the simplified form, let's say, of the function. This will be, it does not go away, it will be a vertical asymptote. So one more time, when the factor goes away, that is a hole in the graph. How do I get the y value? It's going to be a hole. I cannot plug it in the original problem. If you try to plug in 1 here, you'll get 0 over 0, so you don't have an answer. So what we have to do is plug in 1 in the simplified form, and we get -1. So that will be the whole. 1 comma -1. The factor that still stays in the denominator is the vertical asymptote. And if you want, we can graph this function or any other function with a hole in the graph. Okay, now let me explain before we choose a problem. Okay, so let me talk about the slant asymptote. As we know, there are basically 3 types. Vertical asymptote, which as an example is this. A horizontal asymptote, which I don't have to graph, but I'm going to do it anyway. So this will be, let's say, x equals 3. This will be y equals 1. But it's also, there is something called a slant asymptote, which looks like this as an example. Regardless of how what the slant asymptote we are looking at, the function has to approach it asymptotically, like this, for example, and like this. Like this, for example, I don't know, and like this. What about this one? Whatever, but it has to approach it asymptotically, either like this or like this. So at infinities. So as you see, all this discussion is at infinity, right? Either when x approaches the number and the function blows up, or when the function values approach infinity or negative infinity and they approach a number. And the same thing here. As x approaches infinity, the function gets closer and closer to the slant asymptote, asymptotically. Same thing on the other side. Now, no function can have these both. No. So I can have a vertical asymptote with slant, or vertical asymptotes with a slant. I can have horizontal with vertical, but never horizontal with slant. So then which rational function has a slant? The one with degree n in the numerator and degree n in the denominator. Let me write it better like this, and n plus 1 in the numerator. Only when the degree of the top is exactly by 1 unit bigger than the degree of the denominator. So let's say degree 3 over degree 2, or degree 5 over degree 4. Degree 3 over degree 1 does not have a slant asymptote. Why does this happen? Because you understand that this is a line, like y equals x plus 1, for example. So when you divide this by this, I have to get a line. When I divide degree 3 by degree 2, I will get degree 1. When I divide degree 5 by degree 4, I will get degree 1. But when I divide degree 3 by degree 1, I get degree 2, which is not a line. So that's always easy to remember, I think. Okay, So everything else is the same, everything gets determined in the same way, but the slant asymptote, we will be using either long division or synthetic division to find the slant asymptote. We have to use either long division or synthetic division. And this is the end of 4.